on combustion process, which is split into combustion for spark ignition engine, and the other one is compression ignition engine. So there's two sub-chapters under combustion process. Also, by next week, I will be giving you some exercises for you to start practicing for your final exam. And also concurrently, I will also pass you the assignment 2 question next week. So next week, will be no classes. It's just I would urge you all to practice the exercises. So the exercises, I will provide the solution as well. And number 2, next week, I will also pass you assignment 2 question for you to do lah, assignment 2. So next week, no classes, but I will pass you some work for you to do. That is one. Let's move on with this chapter first. And as we move, but hopefully by end of this chapter, we'll talk more about next week, activities for next week. So first of all, we'll go through the combustion for spark ignition engine. Okay. Now combustion, it's clearly, even though that there's a difference between 4-stroke cycle of spark SI engine and also CI engine. Same goes with the combustion. Okay, there's a slight difference. Okay. Obviously, if we can recap back on spark ignition engine, there's two things that which signifies SI engine against CI engine. Okay, spark ignition engine first is using spark plug. Okay, CI engine doesn't use spark plug. Okay. The second one is a spark ignition engine. The combustion is being triggered by the spark plug. Okay, it requires a trigger. Okay, or it requires a ignition. Okay, whereas on CI engine requires the certain factors that is required to start the combustion, which is the ignition. Now it has to the compression ratio needs to be high, pressure needs to be high, and most importantly, the fuel needs to have the self-ignition temperature needs to be low. Okay, in order for the combustion to start in CI engine. But let's dig more further into the combustion process. We'll start with the SI engine first. Okay. So combustion process in general may be defined as a relatively rapid chemical reaction. Okay. In other words, if you put it into layman terms, it's an explosion. Okay, between carbon and hydrogen, which is present in the fuel or petrol. Okay, and also of course, this one everyone knows, we require the oxygen. Okay, for it to burn. Okay, resulting, because the fact that there's a chemical reaction between the fuel and also the oxygen and the air, resulting a liberation of energy. Okay, there's a release, there's an explosion, okay, of energy in the form of heat. Okay, in the form of heat. Now, as an engineer, okay, as an engineering student, whenever we say heat, we always refer to energy. Okay. Now, combustion requirements. Some of what do you require for the combustion to start? Okay, there must be a presence of combustible mixture between fuel and also air. Okay, it doesn't work without air. Means of combustion initiation, okay, or self-ignition, or it's either. So the means of combustion initiation is through the spark plug, okay. Self-ignition is through the CI punya diesel punya fuel characteristics. And then you need to have a stabilization and propagation of flame in the combustion chamber. Okay, stabilize, I'm sure you understand the word stabilize. Propagate, in other words, if I can put it into layman terms, it's the spread. Okay, spreading. Okay, so these are the main components of basic combustion. You need to have air, you need to have fuel, and of course you need to have spark in the case for spark ignition engines or SI engine. So these components, along with other other specific conditions, are needed in order for the basic combustion to occur. Now let's talk about ideal combustion, which in reality it doesn't happen, but let's talk about ideal combustion. Okay, a perfect combustion, in reality it doesn't happen. This is just to understand what is the benchmark, what we are targeting, what we want to achieve, even though we cannot achieve. Okay, but we still need to know what is the perfect combustion. It is only occur when hydrocarbon would be oxidized into water, okay, and carbon dioxide. Okay, so this is basically a breakdown of the hydrocarbon into H2O and also CO2. Okay, also nitrogen would pass through the combustion without being affected. So in other words, if the hydrocarbon or the fuel goes into combustion, it is at 100% being converted, equally split between water and also carbon dioxide. Okay, and during that combustion process, the nitrogen, which is included in the air that passes through the combustion chamber, after all the combustions and explosion happen, it doesn't affect at all. Nitrogen would just pass through. It's just a free ride for nitrogen lah. Now, the fact that when we have in perfect conditions, we only have three emissions, which is water, okay, we have carbon dioxide and also nitrogen, only in ideal combustion or perfect combustion. So the combustion process of SI engine, let's talk about SI engine, can be divided into three broad regions. Now, whenever we talk about combustion in spark ignition engines, okay, if you can imagine the combustion itself, okay, from the point of where the combustion starts until the combustion ends, okay, during the in between the compression and also in between compression stroke, power stroke and also exhaust stroke. If you can imagine the combustion process, it is split into three phases. Okay, split into three phases. One, the first phase of the combustion, okay, the earlier one is what they call as ignition and flame development. Okay, ignition and flame development. And the second phase is the flame propagation. Okay, this is the middle phase. And the last phase is the termination flame. Okay, or flame termination. Now, the words explain itself. Okay, the first phase is where the ignition starts, flame starts to develop. Then comes the second phase, which is the propagation of the flame. Okay, or in other words, the spreading of the flame. Flame already starts and it starts to spread across the combustion chamber area. Okay. Now the third phase, which is the flame termination. So everything that comes into life needs to end. Same goes as combustion. It's like our life lah. We were born towards one day we will die. Okay. So sad story. So the combustion in this last phase, which is the third phase, is the termination of the flame. So the flame or the combustion starts to slow down. It starts to phase down. Okay. Now, flame development is generally considered the consumption. Okay. During this first flame development, it is generally considered as the consumption, whereby the 5%, okay, 5% of the total air fuel mixture that enters the combustion chamber. Okay, that is the so during the first phase, only 5% is being consumed. Okay. So during the flame development, which is the first phase period, ignition starts, okay, ignition occurs and the combustion process starts, okay, but very little pressure rise, okay. There's a slight increase of pressure inside the combustion chamber, okay, and you can hardly notice this. It's less obvious because if you observe the pressure rise, okay. And during this time, because the fact that there's no pressure or very little pressure is being created, there's not much of work being produced, okay. So that is flame development. So figure below, if you could plot the amount of pressure during the combustion process against crank angle. So the earlier phase would be the phase 1, which is the ignition and flame development. And then you have the second phase. I'll show there's a more detailed graph in the following slides. And then during the second phase, which is the flame propagation, is where you have the maximum pressure. And then once the pressure starts to go down, it starts to die off. This is what they call as flame termination. So the increase in pressure rise is very slow after ignition, okay, during the flame development period. So the kickoff or the ramp up of the pressure immediately after the ignition is slightly slow, okay, slightly slow. So maximum pressures usually occurs at 5 degrees to 10 degrees after TDC. So this is really important. So this statement, okay. Now, in any particular engine, what you want to have of whatever the maximum pressure that the engine can produce, okay, this is really important, okay. Of whatever the maximum pressure that the engine can produce, the maximum pressure needs to be in between 5 to 10 degrees after TDC. Okay, so in other words, this peak, okay, of whatever the maximum pressure value is, needs to be 5 to 10 degrees after TDC in order for you to maximize the power being produced. Okay, then comes the story of how can you actually vary the maximum pressure. Okay, if it's too early, how do you like shift the peak to go early or later? I will explain to you that in the later slides. But definitely the ultimate aim is basically to have your maximum pressure always 5 to 10 degrees after TDC. Okay. So in other words, 5 degrees to 5 to 10 degrees after TDC is when your piston have passed through the TDC and starts to go down to BDC. It already starts to move from TDC to BDC. So just about all useful work produced in engine cycle is the result of the flame propagation, which is your second phase. Okay, most of the work is being produced during the second phase. This is the period when the bulk of the fuel and mass is burned. Okay, 80 to 90% of the air fuel mixture is being burned during the second phase. During this time, pressure in the cylinder is greatly increased. Of course, this is when you have your maximum pressure, thus provide the force to produce work in the expansion stroke, which is why you need to have your maximum pressure, okay, in the second phase. Okay, and also the maximum pressure needs to be 5 to 10 degrees after TDC. Okay. So the final 5%, some sources would say 10% of the air fuel mixture is being burned in the last phase, which is the flame termination. Okay, so you have during the first phase, we have between 5 to 10% air fuel mixture being burned, and then you have the second phase, which is most of the air fuel mixture is being burned by 80 to 90%, and the rest remaining between 5 to 10% is being burned in the last phase, which is the flame termination. So during this time, pressure quickly decreases, okay, in the flame termination, and combustion dies off or stop. So in SI engine, combustion ideally consists of exothermic subsonic flame progression, okay, through a premixed homogeneous air fuel mixture. So this is how the combustion behave, ideally should behave. So the spread of the flame front is greatly increased by the induced turbulence, swirl and squish within the cylinder. So this relates back to the necessity to have a good fluid motion, as what we already covered last week. Okay, now this is the main reason, because the turbulence, swirl and so squish effect of air does affect on the flame front in your second phase, okay, which is the flame propagation. So the more flame propagation or the more aggressive you can actually have in your second phase, that would actually would be resulting more work output lah, or power output. So if you can, based on the pressure profile of the combustion, okay, against prime angle, so this is a more clear picture compared to the previous one, where it shows the phases, okay, between phase 1, which is the ignition and also flame development, and then you have the second phase, which is the flame propagation, and then you have the lastly, which is the final stage, final phase, which is the flame termination. So if you look at, if you can imagine, okay, so in the, let's say that if your ignition or the spark plug starts to trigger at point A, okay, point A over here, and then that would signal that the first phase, which is the ignition and flame development, starts to happen. Okay, and then once the ignition starts to trigger, so the pressure slightly increases. Okay, but before that, before A, okay, there's an increase of pressure. So this increase of pressure, okay, before A, point A, is because of the reduced volume, okay, between reduced volume by the with the piston movement from BDC to TDC. But after A, which is the ignition, the combustion starts to happen, okay. But during this phase, okay, which is the phase 1, ignition and flame development, so the pressure starts to slightly increase from A to B. So the trend, you can see that the pressure increases at after A, it slightly increases to B. So during this A to B is what they call as, or another word for it is ignition delay or ignition lag, okay, which is A and B. Now after B is the second phase, where you could actually notice that the pressures aggressively increases, okay. This is the flame propagation, okay. This is when your peak pressure would be achieved, okay. So the maximum pressure is from point B to point C, and then immediately after the peak pressure, the pressure starts to go down. So whenever the pressure starts to go down, this is when this is what they say as the flame termination, which is the last phase. So it moves from C to D, from C to D. So this is when your combustion starts to dies off, okay, or what they call, or sometimes they call it as afterburn. So there you have 3 phases, okay, of combustion process. So whenever we refer to combustion process, there's always 3 areas for you to discuss, okay, or explain. So let's go into detail in each of the stages, okay, or phases, okay. In the first stage, which is ignition and flame development. So ignition lag or ignition delay can be defined as, this is the time interval between initiation, or whereby the spark starts to trigger, and the actual starts to combust, okay. Actual combustion, yes, slightly starts initiated in the first phase, but the true combustion actually lies in the second phase, okay. It is a very small fraction of second during which the fuel air mixture is chemically prepared for reaction. Therefore, the initial delay period can be calculated as follows. So in other words, you can actually calculate your first phase of combustion, or you can actually calculate your ignition and flame development phase. Okay, this is basically of how you can calculate. So you can actually calculate the period or the initial delay, or the period of the first phase, or some are known, some of the first phase is also known as initial delay period lah. Okay, so it is calculated by degree of engine rotation, okay, divided by 360 times engine speed divided by 60. Okay, degree of the engine rotation is basically your crank angle. Okay. Now, during this stage, generally about 5 to 10% of the fuel air mixture is consumed under normal operating conditions. So you would expect that whatever air fuel mixture that goes into the combustion chamber, of whatever the amount is, 5 to 10% of that volume, okay, will be consumed during the first phase. Only 5 to 10%. Okay. So the event took place during this period. Ignition occurs and initiated by spark. Okay, and this one we all know. Okay, so combustion process start as air fuel mixture is ignited, okay, by the spark plug in the immediate vicinity of the spark, okay, close surroundings, or in other words, the combustion actually triggers or starts from close to the spark plug, okay, forming a small halo nucleus of flame like a form of soap bubble sphere. Okay, so combustion reaction starts to spread out. So combustion starts actually close to the spark plug, and it starts to spread in the form of a circle or sphere. Okay, outwards. Okay, away from the spark plug into the remaining volume of the cylinder. So it spreads out to all of the open area in your combustion chamber. So at this stage, the rate of combustion is low, which result in low rate of pressure rise. Okay, therefore, there's not much of work being produced. Okay, so it's very weak. Okay, it's very, very weak. The reason behind such slow progress in combustion process is due to low turbulence motion in this zone, as well as high heat losses, okay, relatively to co-spark plug materials or gas mixture. Flame is generally detected at about 6 degrees of crank rotation after the spark plug triggers. Okay, this means that there is a time interval where combustion starts after ignition occurs, where we call this as delay period. So by the time 5 to 10% of the air fuel mixture has been burned, which is the duration of the first stage, the combustion process is then well established, and the flame front starts to move faster as it penetrates into the second phase. This indicates that the combustion has entered the second stage, which is the flame propagation. Okay. However, the first stage ends where the second stage start is very difficult to specify due to many variables involved, and therefore this can be specified for a particular engine from indicator diagram study of this particular engine. The first two stages of combustion are not entirely distinct since the nature and velocity of the combustion changes gradually. However, we can assume that the end point of the first stage itself is the beginning of the second stage. Okay, so this point can be specified when a first measurable rise of pressure is seen in the indicator diagram, which is the diagram that we refer to in the previous slide. The point where the line in combustion depart from the line of compression as shown in the following diagram. So if you could see anything, if you can see the curve before point A, we can say that the increased rate of increase of pressure, we can say it's quite consistent. But after the ignition occurs at point A, the pressure slightly, the rate of pressure slightly increases. But as it passes point B, entering into the second phase, you can see the pressure, the rate of pressure significantly increases. Okay, so we can actually determine by just looking at the graph. Okay, now let's move into the second phase, which is the flame propagation. This is where the flame starts to spread. Okay, so as the first stage ends, okay, remember that during the first phase, the combustion is very weak. Okay, now is the strongest combustion phase, which is the flame propagation. So the combustion of this mixture inside the cylinder becomes more established. Okay, it's more established, where the rate of pressure rises aggressively, becoming more faster. Okay, and therefore provide higher force to produce work. Okay, most of the fuel air mixture is being burned during this phase, which consumes 80 to 90%. Okay, most of the useful work is produced in this work. Okay, most of the useful work. Okay, how do you know? It is related to of how much the fuel air mixture is being consumed. So more fuel air mixture being burned and more being consumed, so more work is being produced lah. So during this stage, the gas mixture undergoes a motion of turbulent swirl squish, okay, resulting in a high flame front speed. So during this stage, this is the fastest the flame travels. Okay, so the flame front expands spherically, which initiated in the first phase, but in the second phase, the flame front starts to expand more faster, much more faster, and spread out throughout the combustion chamber. Okay. So as combustion proceeds, the gas mixture pressure rises to high values in reaching the maximum peak pressure. However, the temperature of the burnt gases behind the flame front is higher than before the flame front. Okay, so if you could imagine the spread of the combustion, okay, flame front is the furthest away from the spark plug, has the highest temperature, okay, compared to the previous position of the flame front. And therefore, density of the burnt gases decreases and thus expands to occupy a greater volume. Okay. This volume increases of the burnt gases compresses the unburned gases, and therefore the unburned gases will be subjected to compressive heating. And due to heat transfer, either through radiation, conduction, or convection, will further increases the unburned gases temperature as well as its pressure. Okay. So from these conditions of operation, the flame moves throughout the combustion chamber and travels progressively, increasing temperature and pressure at the same time, thus improving the combustion itself by reducing the chemical reaction time and also increasing the flame front speed. So when the piston reaches TDC, 2/3 of the air fuel mixture is completely burned. Okay, gases, okay, temperature and also pressure reaches the maximum values. Okay, which is why you need to have your maximum peak pressure at between 5 to 10 degrees after TDC, and all mixture is completely burned at about 15 degrees at TDC. By right 15 degrees after TDC, all the fuel air mixture, okay, has been completely burned. Okay, in other words, 80 to 90% has been achieved at 15 degrees after TDC. So in addition to the effects of turbulence, fuel and squish on certain engines by design, the flame speed depends on the type of fuel and also the air fuel ratio. So lean mixtures have a slower flame speeds. Okay, which is why in order for you to have a slightly more power, okay, you would actually have a slightly richer air fuel mixture. But ultimately, based on the type of fuel, petrol that we are using in the real world today, lambda of 0.9 would be producing the best combustion. In other words, the best power. Slightly rich mixture have the fastest flame speeds. Okay, remember, faster flame speed produces more work. produces more power, with the maximum for most fuels occurring in equivalence ratio between 1.2. So in other words, it's roughly about lambda 0.9. Exhaust residuals and recycled exhaust gases slows the flame speed. So this is what exhaust residual and recycled exhaust gases mean, is basically exhaust gases that is being trapped from the previous cycle, which is which is trapped in the combustion chamber and didn't escape out of the combustion chamber through the exhaust valve. There are a small portion of these residual gases being trapped in the combustion chamber. Flame speed increases with engine speed due to higher turbulence, swirl, and squish. So as the engine speed increases, the characteristics of the air fuel mixture that enters the combustion chamber has a more is more towards turbulence, swirl, and or squish, which actually assists to increase the flame speed. Combustion period in degrees is better known as burn angle, so which can be defined as burn angle is the angle through which the crankshaft turns during combustion process, or it is the number of crankshaft degrees combustion process occupies. In most engines, typical values of burn angles is between 25 degrees. Okay, so accordingly, if combustion is to be completed at 15 degrees after TDC, so this is when in the case of where combustion totally dies off at 15 degrees after 15 degrees after TDC, then ignition should occur about 10 degrees before TDC. Okay, so in between 10 to 15, that would be your burn angle. Okay, so I hope that you are clear on that. So if in the case of whereby if the ignition starts 10 degrees before TDC, and if it has a 25 degrees burn angle, then definitely you know that the combustion finishes off at 15 degrees after TDC. Okay, so that's how you get your burn angle. Start of ignition, or in other words, okay, this is the correct term where the spark plug triggers. Okay, this is the correct term. Start of ignition, or the abbreviation of it is SOI. Okay, if the ignition starts too early, the pressure decreases rapidly, okay, to reach a desirable level before TDC. If it's too early, then you are shifting your peak pressure at a much earlier, and therefore you cannot achieve the you cannot have the peak pressure at between 5 to 10 degrees because your ignition starts too early. If it's too late, then you're shifting your maximum pressure way later than after 10 degrees. Then therefore you need to know, therefore in order for you to control your peak pressure at exactly in between 5 to 10 degrees, the means of doing that is by controlling your ignition, start of your SOI. So normal time from above, ideal time of ignition usually is in the range of 10 to 30 degrees before TDC. So in other words, yes, in normal automotive engine nowadays, what is the range of spark? What is the range of ignition timing, or what is the range of SOI? In automotive engines, you are looking between 10 to 30 degrees before TDC. So if you have the time, if you are able to, if you have the opportunity to open ECU calibration files, you should be able to see the ignition base map, okay? And most of the ignition base map, all cars mostly, is between 10 to 30 degrees. Mostly, not all. So start of ignition, best performance will be achieved when the greatest portion of the combustion chamber takes place near the top dead center. Or in other words, the best performance will be achieved if you have your peak pressure in between 5 to 10 degrees after TDC. If the spark is not advanced enough, the piston will already be moving down when much of the combustion takes place. Okay, this is too early. In this case, we lost the ability to expand this portion of the gas through the full range, decreasing the performance. But if the ignition is too advanced, okay, sorry, just now was too late. Okay, now is if the ignition is too advanced, then too many of the gases will burn while the piston is still rising, okay, still moving towards TDC. As a result, the work that must be done to compress this gas will decrease the net work produced. Okay, so just imagine if you have the peak pressure at exactly where at the condition of where the piston is increasing from BDC to TDC. So that would be not ideal lah. Okay, but if the ignition is too late, okay, so by the time the peak pressure starts to happen, and during this time the piston already move far away from TDC, then it's not that then the power or work that is being produced is not that efficient. Okay, has to be in a ideal timing. So if ignition timing does not become advanced enough, most of the combustion occurs when the piston is moving down. In this case, the power and the thermal efficiency decreases. If ignition timing gets too advanced, most of the air fuel mixture burns before the piston rise. Additionally, the period of the time of the heat losses becomes larger than the net work, and the thermal efficiency also decreases. So by raising ignition advance, however, an increase in temperature and pressure in cylinder happens. Okay, if you put your SOI too early, okay, your pressure will increase and your temperature will also increase. Okay, but the power and the thermal efficiency decreases due to the high friction losses and other losses in the engine. So the performance of SI engine highly depends on the initial timing. Okay, this is how this is the means of how you want to control your cylinder, control your combustion. Okay, its optimum value should be determined for each SI engine. So different engine has a totally different characteristics. Okay, but generally they are same. Generally the same. Their characteristics are the same, but the values will not be the same. Okay. So for this engine, the maximum thermal efficiency and net work are obtained at 31 degrees crank angle before TDC. Actual spark timing is typically between 10 to 30 degrees before TDC, but to specify exact position depends on what is the fuel you're using, what is the engine geometry or the engine design, at what speed the engine is running, and so on. So it varies. Okay. Considering the engine speed factor, it can be said that combustion occurs faster at higher RPM due to better mixing and various mixture motion inside the cylinder by the swirl, turbulence, and also the fluid motions. Okay, real time for combustion process decreases as RPM increases also due to good mixing caused by turbulence flow effect. So real time for engine cycles also decreases as RPM increases. Okay. From 1 and 2 above means that burn angle remains almost the same as time factor equalizes both factors. Okay. So that is basically on the second phase, which is the flame propagation. Now moving on into the third stage, which is the final phase for flame termination. In this stage, the remaining air fuel mixture, which is approximately 5 to 10%, is being burned, which makes it the final mass of fuel to be consumed. Okay, and a little additional work is delivered, not much. Okay, this means that 90 to 95% of the mixture is already being burned in the second phase, and therefore the rate of pressure rise quickly decreases and combustion ends at about 15 to 20 degrees after TDC. So the last 5 to 10% during this phase is compressed into few percent, about 2% of the combustion volume. So just imagine of whatever the combustion volume is, only there's only 2% of the volume is being compressed. Okay, this volume is at the extreme corner of the combustion chamber. Okay, this only happens during the final phase. Okay, the piston starts to move away from TDC to DDC, volume increases, uh, and resulting the air fuel react in a very small volume. So because the combustion starts to die off, okay, and therefore the reaction takes place at a very low rate. So the flame speed starts to decrease, the pressure starts to decrease, temperature starts to decrease, and so everything starts to decrease. So near the wall, the mixture motion is damped out, and the combustion chamber wall act as a heat sink. It absorbs the heat, okay, which causes the rate of reaction in further reduced. Flame speed is reduced. Combustion ends by slowly dying away. Okay. So that is pretty much on spark ignition engine. Before we finish, we continue into CI engine. Is there any question? Okay, tak ada question ya? Okay, kalau tak ada question, we'll take a break for 10 minutes. We'll continue back at 9 o'clock. Okay? So, nak cakap ni. So, we'll take a break. We'll continue back at exactly at 9 p.m. See you. Okay, guys, 9 p.m.
Okay, Doktor.
engine is triggered by the self-ignition temperature of the fuel. So, but other than that, roughly the process is roughly about the same. So let's go through very quickly on CI engine, because the fact that we've already understood on combustion in SI engine. So in SI engines, flame front moves through a homogeneous mixture, while CI engines are unsteady process occurring simultaneously at many spots in a very non-homogeneous mixture. Okay, and this is actually controlled by the fuel injection. So as what I said in previous chapters also in CI engines, the amount of power in diesel engines or CI engines is basically controlled by the fuel injection, because the fact that fuel injection actually controls your controls the combustion process in CI engine. So air intake is unthrottled in CI engines, giving almost atmospheric intake pressure. So it's always like non-restrictive flow, and this reduces the pumping losses, okay, because the fact is not being not throttled, and the fact that it also improves the thermal efficiency. So air only to be compressed during most of the compression stroke, while fuel is injected into the cylinder towards end of the stroke, okay, during the compression stroke. So injection span for about 20 degrees, starting 15 degrees before TDC and lasting up to 5 degrees at TDC. So if you notice that in SI engine, we are concerned about the when does the spark triggers, but now in CI engine, we are more concerned on when does the fuel is being injected. Okay, it is more concerned on when the fuel is being injected. So delay period is almost constant in real time. So at higher RPM, okay, fuel injection must start earlier in the cycle, okay, because of whatever the condition the engine operates, the delay period is always the same, okay. So air movement, turbulence and swirl and high injection velocity is needed to spread the fuel droplets throughout the cylinder and forces to mix with air, okay, which is why the fuel, diesel fuel is that is injected needs to be at a higher pressure. After the engine is provided with the air fuel mixture, the combustion process is set to be started, okay. Air only is emitted into the engine cylinder during the intake stroke, then compressed during most of the compression stroke, near the end of which the fuel starts to inject. So due to high compression ratio, okay, we already know that diesel engines or CI engines has a higher compression ratio compared to SI engine, the mixture temperature starts to rise, okay, and reaching a level high enough to make the fuel, the air mixture, to ignite by itself, okay. This temperature is what we call as SIT lah. We already covered this one. So the principles of ignition in CI engine is that the mixture needs to be compressed, okay, needs to be compressed, which is why you have high compression ratio, okay, to raise its temperature up to SIT. So diesel engines, CI engines requires a high compression ratio to make sure that it compresses the air to raise the temperature, to raise the temperature so that the SIT can be achieved, and hence starts the ignition. So after injection, fuel must undergo series of events to ensure proper combustion, which is atomization, vaporization, mixing, self-ignition, and also combustion, okay. So the combustion process starts with the atomization. Fuel drops break into very small droplets, okay. This needs to be this can only be achieved if the pressure is high enough, okay. The smaller the original drop size emitted by the ejector, the quicker and more efficient it atomizes with the air. Okay, so therefore in CI engine, the fuel pressure needs to be very high in order to get small droplets. Okay, then is the vaporization. So it's the small droplets which is that has been injected needs to evaporate with the fuel. It has to mix, okay? Because if it doesn't mix, then it's not efficient. So this occurs very quickly as soon as the fuel is being injected due to the raised air temperature. Raised because the fact that it's already temperature has already been the pressure has already increased. Okay, which and if in the case of where the temperature doesn't reaches a certain value, the vaporization will fail. Okay. Vaporization, high air temperature needed for this vaporization process requires a minimum compression ratio in CI engines of about 12 to 1. That is a nominal value lah. Okay. So about 90% of the fuel injected into the cylinder has been vaporized within 0.001 second after injection. So this is basically the ideal vaporization time or period. As the first fuel evaporates, the immediate surroundings are cooled by evaporative cooling. So as soon as the fuel is being injected, it cools down the combustion chamber immediately. Okay, this greatly affects the subsequent evaporation. So near the core of the fuel jet, the combination of high fuel concentration and evaporative cooling will cause adiabatic saturation of fuel to occur. Evaporation will stop in this region, and only after additional mixing and heating will this fuel be evaporated further. Then comes the mixing. Okay, after vaporization, the fuel vapor must mix with the air to form a mixture. Okay, this mixing comes about because of the high fuel injection velocity added to the swirl and turbulence in the cylinder air. Next figure shows the non-homogeneous distribution of air-fuel ratio that develops around the injector fuel jet. Combustion can occur within the equivalence ratio limits of 1.8 and 0.8. Okay, lean and so forth. So that is basically shows the mixing and vaporization of the fuel droplets. So the liquid core is surrounded by successive zones of vapor, which are, in the case of if it's too close to the center, it will be too rich to burn. As it travels away from the center, it reaches rich combustible, C is stoichiometric, and D lean combustible, and lastly too lean to burn and so forth. So self-ignition starts mainly in zone B, which is rich combustible. Okay, solid carbon soot is generated mostly in zone A and B because the fact that A is too rich, so there are unburned fuels which created solid carbon soot. Okay. Then you have the self-emission at about 8 degrees before TDC, 6 to 8 degrees the range after the start of injection, air fuel mixture starts to self-ignite. Okay, actual combustion is proceed by secondary reaction, including breakdown of the large hydrocarbon molecules into hydrogen and also carbon into smaller pieces and some oxidation. So this reaction caused by the high temperature air inside the combustion chamber are exothermic and further raises the air temperature in immediate local vicinity. So this finally leads to actual sustained combustion process. And lastly, this is when you have the true combustion. Combustion starts from self-ignition simultaneously at many locations and slightly reaches zone at fuel jet. So you are looking at multiple combustion, okay, in several locations inside the chamber, where the equivalence ratio ranges from 1 to 1.5 in zone B. So at this time, somewhere between 70 to 90% of the fuel in the combustion chamber is in the vapor state. So when combustion starts, multiple flame fronts spreading from the many self-ignition sites, it quickly consumes all the gas mixture which is in correct combustible air-fuel ratio, even where self-ignition wouldn't occur. So this gives a very quick rise in temperature and pressure within the cylinder during the combustion phase. So you can see that this is basically the profile of the cylinder pressure plotted against the crank angle is the start of the fuel injection. Okay, if you compare with if you can recap back on SI engine, okay, we are more concerned. A is the start of ignition, or this is where A is where the spark plug starts to trigger. But on CI engine, A is the start of fuel injection, and C is the end of fuel injection. So the injection starts from A throughout until it reaches the peak temperature, peak pressure, sorry. And B is where the combustion starts to increase, starts to develop. You could notice that the amount of pressure, rate of pressure, significantly increases as it after B. So A and B is what they said as the ignition delay. A and C is the total fuel injection period. Okay. Combustion, the higher temperature and pressure reduces the vaporization time and ignition delay for additional fuel particles. So the higher the temperature and pressure caused by the compression ratio, vaporization time and ignition delay also reduces, which is good. Okay. This causes more self-ignition points to further increase the combustion process. So as much as possible, you want to have a shorter ignition delay. Okay. Liquid fuel is still being injected into the cylinder after the first fuel is being already burned. After the initial start of the combustion, when all the air-fuel mixture that is in combustible state is quickly consumed. The rest of the combustion process is controlled by the rate at which fuel can be injected, atomized, vaporized, and fixed into the proper air-fuel mixture. So in other words, you need to totally control your fuel in order for you to manipulate your combustion. Okay. So this rate of combustion, now controlled by the fuel injection rate, can be seen in the cylinder pressure versus crank angle figure in the slower pressure rise that occurs after the initial fast rise. So the combustion usually lasts between 40 to 50 degrees of engine rotation and much longer than the 20 degrees of fuel injection rate. So this is because some fuel particles takes a long time to mix into the combustion mixture with air. Okay, it requires time, and combustion therefore lasts well into the power stroke. Okay, so that the combustion actually extend, okay, into the power stroke. Okay. So this can be seen in cylinder pressure figure, where the pressure remains high until the piston reaches 30 to 40 degrees after TDC. About 60 degrees of the fuel is being burned in the first third of the combustion time. Burning rate increases as the engine speed increases. So does the burn angle. So that the burn angle remains about constant throughout the engine speed. So the burn angle actually remains the same. During the main part of the combustion process, anywhere from 10 to 35% of the fuel vapor in the cylinder will be in a combustible mixture. So this is when you can see that A is where the fuel injection starts to initiate. Okay, A and B is the initial delay. As it passes B, okay, pressure starts significantly increases. Okay, towards C, and C is the uncontrolled combustion stage. But C and D is where the fuel injection starts to remains and a fuel is remain being injected between C and D. This is where you control the combustion. Okay. and D and E is where you have the afterburn stage. So pretty much on the base, you can have refer to the basis of from the SI engine, but in CI engine, you have you need to control the fuel from the beginning until it reaches the uh, peak pressure of the combustion. Okay. So combustion process by the following stage. You can just go through each of the process. Initial delay A and B, premix uncontrolled combustion phase, which is B and C. A, B, B, C. You can always refer to where does it is positioned in the graph here. C, D is the mixing control combustion phase, and DE, which is the afterburn, is the late combustion phase. Okay. So initial delay period of about 0.4 to 3 milliseconds will be considered normal when air fuel mixture in the combustible ratio, temperature of the mixture in the SIT range. Okay. So if the fuel, if the injections strategy is designed for certain fuel that has a certain SIT range, in the case of where you change the fuel, then with a different SIT range, then definitely it will affect your combustion. Okay. So initial delay decreases when any of the following parameters increases. Okay. So if you increase the temperature, if you increase the pressure, if you increase the engine speed, if you increase the compression ratio, and if you increase, if you are operating the engine at much higher RPM, the initial delay will decrease, okay, as much as possible. So injection rate that has no real effect on initial delay, but initial timing has a marked effect as when injection starts. So if it's too early, initial delay time increases due to low in terms of due to low temperature and also pressure. If it's too late, okay, then initial delay will increases and piston moves well past TDC during the uncontrolled combustion stage. Okay, so due to many reasons, initial delay period may be a long initial delay, short initial delay, and normal initial delay, so forth. Now let's talk about the cetane number of fuel and also initial delay. So low cetane number causes the initial delay to be too long. Okay, so certain fuel has characteristics of low cetane number, certain fuel has a high cetane number. As more fuel will be injected before combustion, and so when combusted results in high initial pressure rise, large initial force on piston, and rough engine operation. So these are some of the effects of lower cetane number. Whereas on high cetane number fuels, okay, initial delay will be much more shorter, causing combustion starts too early. Okay, if its cetane number is too high, then it will cause the initial delay to be too short or too early before TDC, and this also causes power loss. But definitely, which is why the cetane number needs to be correct. The normal range for cetane number of diesel fuels is between 40 to 60. Okay. So that is pretty much on what we have already covered on both CI and also SI in combustion. Okay. So is there any question for today? Okay, if there's no more question, yes.
Thank you, sir.
Any question? No.
No, sir.
Okay, right. So if there's no more questions, I will try to brief you what's the plan for next week's activity. In a couple of days, just before next week's session, I will pass you exercises for you to practice. Okay, these exercises are actually meant to prepare for your exam and also your testing. Okay, so these are I will provide you the solution as well for, and also some I will provide you with answers only. Some of the exercises I will provide you with the solution. Okay, just need to spend time next week to practice on the exercises. In a way, you are actually doing a revision lah by doing the exercises. Okay, and also by next week also I will pass you your question for assignment 2. So by the time so the official date for you to start your assignment 2 is next week. Okay, and then once you have your assignment 2 question, then you have 2 weeks to submit. Okay, so that's the plan for next week lah. So next week session, there won't be any classes, but I would want you all to practice the exercise and also start your assignment. So the documents I will include in e-learning lah, as usual. Okay, any question? Okay, if there's no more questions, let me just pass you the attendance list for today. Give me a moment. So I've already put the link for your attendance in the chat box. But other than that, we are good for today. Thank you very much for your attendance. Thank you very much for your attention. If you have any questions, please do email me or WhatsApp me. But other than that, Assalamualaikum warahmatullahi wabarakatuh and good evening to everyone. Thank you very much. Bye bye everyone.